This webcast will work through some problems that involve uniform circular motion and centripetal force. Okay, so I am in worksheet 7A, and we'll just start with the first problem. So first we have a person on a bicycle moving around a circular track at a constant speed of 22 meters per second. The diameter of the track is 18 meters, and so we'd like to find the period of the bicyclist, which means how much time it takes them to move one complete trip around the circle. So we have a formula for that, which says that the period, t, equals 2 pi r, that's the circumference of the track, divided by the velocity. Now I do need to find the radius of this track. That's going to be the diameter divided by 2, half the diameter. So it will be 18 meters divided by 2. And then I think we're ready to plug into this formula. So we've got 2 times pi times the 9 meter radius divided by the 22 meters per second speed. And if we do this math, we can find how long it will take to make one complete trip. So 2 times pi times 9 divided by 22 is 2.570 seconds. Okay. Let's do another one. Here we've got a runner on a circular track. They're giving us the radius of the track, and his constant speed is 5.25 meters per second. So first they ask how long will it take the runner to move around the track one time. Well, they're asking for the period, because the period is the time to go all the way around the circular path one time. So period would be the circumference divided by the speed. And so here, 2 pi, they've already given me the radius, so no need to change that. And the speed is 5.25 meters per second. And so let's see. And so it will take them 28.723 seconds to make one full trip around that circular track. Then it asks for the radial acceleration of the runner. Well, the radial acceleration is proportional to the square of the velocity divided by the radius of the path. And so the velocity is 5.25, and we're going to square that and then divide by that radius. And the radial acceleration is 1.148 meters per second squared. Okay. Let's talk about number 3. So Jupiter has an average distance from the Sun of 7.78 times 10 to the 11th meters. So here is Jupiter, and Jupiter's making a circular path around the Sun. The distance between Jupiter and the Sun is like the radius of that orbit. So the radius here is that distance of 7.78 times 10 to the 11th meters. Okay. And we know the time that it takes the planet to make one full revolution. They've nicely given that to us in seconds, which is a standard unit. We'd like to find Jupiter's tangential speed. In other words, whenever we look at it, that speed that's tangential to the circle, what is that speed? So the tangential speed equals the circumference, which is 2 pi r, divided by the period. And everything here was given to me nicely in standard units. And so I can just plug in here. And so the velocity is 13,070 0.4 meters per second. Very fast, right? It has a long way to go, and so it does move very quickly. Let's go on to number 5, where we have an astronaut swinging something in a horizontal circle. And so, they've got something that's tied to a rope maybe, and they're swinging it in a circle. The circle has a radius of 0.5 meter, and they're swinging it at 120 RPM. Whenever we see RPM, the first thing we should do is to find the period. So we're going to find the period. That's not one of the questions, but we are going to need the period if we're going to answer the questions. So the period is going to be the inverse of the RPM, but we have to convert minutes to seconds. So we have 120 revolutions per minute. That's what RPM means. 1 minute is 60 seconds. And I'm just converting to revs per second, and I'm taking the inverse because I want to find how many seconds it takes to make one full revolution. And so I get 0.5. So it takes 0.5 second for this object that the astronaut is swinging to go around the circle one time. Okay, so the radial acceleration is the tangential speed squared divided by the radius. Okay, they haven't given me the tangential speed, but I think I can find that, right? Because I know the period now. So that tangential speed would be the circumference divided by the period. Let's see, the radius is 0.5 meters. Oh, look at this, that's meters. The period is 0.5 seconds, so it's basically 2 pi, or 6.283 meters per second. Okay, and so then it says express the object's acceleration in g's, where g is one free fall acceleration near the surface of the Earth. In other words, g is 9.8 meters per second squared near the surface of the Earth. Okay, so the acceleration was 6.283 meters per second. So I'm just going to, oh, I'm sorry, this is meters. Oh, I haven't found the radial acceleration. My goodness. All I have found is the tangential speed. Got ahead of myself. So once I have that, I can find AR is going to be that tangential speed, 6.283 squared divided by the radius, which is 0.5 meters. And so I get 78.957 meters per second squared. That is the radial acceleration. If we wanted to express that as g's, and I'll just do that up here because I'm running out of space, the AR is 78.957 meters per second squared divided by 9.8 meters per second squared, and so that would be 8.057 Gs. That's just a way of normalizing or understanding an acceleration in terms of an acceleration that we are very familiar with. We've all experienced the acceleration due to gravity near the Earth. You know, we've jumped off steps or jumped off low walls, so we've felt that acceleration down to the surface of the Earth. We've all thrown balls and seen how they accelerate as they fall down. And so this particular thing that the astronaut is swinging is experiencing 8 times that type of acceleration. And then part C says find the tension in the string that the astronaut is using to swing the object. Well, that tension force in this case is the centripetal force. And I can calculate the centripetal force as the mass of the object that's going in a circle times the radial acceleration. Well, this little object has a 250 gram mass. I need to convert that to kilograms. That's 0.25 kilograms. And then we found a radial acceleration of 78.957 meters per second squared. And so that tension force must be 19.739 newtons. Okay. Let's go down to number 7 and look at something with a little more difficulty. So here we have a curve with a radius of 23 meters and a banking angle of 15 degrees. So a lot of times when there is a road that has a sharp circular path, the road is banked so that the outer edge is higher than the center edge, and the banking angle here is 15 degrees. So in other words, we've got a car, moving around this circle, and if I look on the end of the car, these are my wheels, here's the body of the car. Okay, one side of the car will be slightly elevated because of that banking angle. When they do this, there's actually a normal force. The normal force that the road is exerting on the car helps to keep the car moving in that circle. Let's do a force diagram so that we can see what forces are there. So I'm just going to do a simple force diagram for this car. So let's see here. So there's going to be a gravitational force on the car that's being exerted by the Earth. And there's going to be a normal force, right? It's going to be perpendicular to this, to the surface of the road. And so it's going to be at an angle here. This is the normal force on the car by the road. And I probably need to break that into its components. So here is the y component of the normal force, and here is the x component of the normal force. I should find that angle, and so I'm just going to show you that if this is my normal force, and here was my 15 degrees, this is also 15 degrees. And this is 15 degrees. Okay. So the car is not moving in the vertical direction. And that means that the net force in the vertical direction equals 0. So Fny is equal to the gravitational force on the car. Okay, those two forces are balancing each other out. I don't have anything balancing the x component of that normal force. Okay, and so I know that Fny would be the normal force times the cosine of that 15 degree angle because it's adjacent to the 15 degree angle. I know that x would be Fn times the sine of 15 degrees. And I know that the centripetal force is going to be provided by that x component of the normal force, because that's the force that is pointing toward the center of the circular path. That is the centripetal force. And a centripetal force is always equal to the mass of the car times its tangential speed squared divided by the radius of the path. Okay, so let's see here. So I guess I can say that this equals m v squared over r. Well, let me do it down here so I go in a logical progression. Since F and y equals the force of gravity, that equals the mass times the acceleration due to gravity. So in this problem, they have not given me the mass of the car, and so, but don't feel like that we're stuck there, because we can take the sine over cosine, and that is equal to the tangent, right? And let's see, since the sine of Fn sine of 15 is m v squared over r, that's on top, Fn cosine of 15 is equal to mg. A lot of things are starting to cancel out here because they're on top and on bottom. And so I get that the tangent of 15 degrees equals v squared over rg. And let's see, I know the r because they gave me that. They said that this curve has a radius of 23 meters, and of course I know g is 9.8. And so I can solve for the v here. It's going to be the tangent of 15 degrees times 23 times 9.8, and then I need to take the square root of that. And so I get 7.771 meters per second.